Okay, welcome. My name is Brad Calder, and I'll be giving a talk on Windows Azure Storage, its data abstractions, and how to use them to build applications for the cloud. So Windows Azure Storage is a service in the cloud offering storage that allows developers, applications, and their users to access this vast amount of cloud storage that's scalable, durable, and available with anywhere at any time access. And this is provided basically as a utility-based service. So you only pay for what you use and store. Now, the three fundamental data abstractions we provide access to are blobs, tables, and queues for constructing and building your applications. And these are available via very easy-to-use REST interfaces as well as simple-to-use storage client libraries. Now, recently, we also made available what we call Windows Azure Drives. This allows your applications to use existing NTFS APIs to access a network-attached durable drive. So what are these data abstractions in a little bit more detail? Well, blobs provide an interface to allow you to store your files into the cloud. So it's a simple interface for storing named files along with metadata for the file. Drives, as I mentioned, allows your applications to mount and access a durable NTFS volume in the cloud. Tables provide structured storage, where a table is a set of entities which contain a set of properties, and you can query over those entities and properties. And queues provide a reliable delivery of messages for your application. So in this talk, I'll go through each of these in a little bit of detail in this order. Now, before you can access any of these data abstractions, the first thing you need to do is go to the Windows Azure Developer Portal, and there you will create a storage account. You create a globally unique storage account representing your data that you're going to store. And when you do that, you choose the geolocation in which you want your data stored in. Currently, we offer 6 locations around the world, 2 in the US, 2 in Europe, and 2 in Asia. So you pick a geolocation to host your storage account, and then all the requests and all the data you store into that account will be hosted in that geolocation. Now, the other important thing you can do here is when you run your service, you can actually also co-locate in that same geolocation with your storage account. And for obvious reasons, you want to do that for low latency and high connectivity, but also the bandwidth between compute and storage in the same geolocation is free. Okay? Now, when you create your storage account, you get back a 512-bit secret key. You then use that secret key to sign all of your requests to the storage service. And that basically sends to the storage service a access signature, which we then authenticate on the storage service to authenticate the request. Okay. So let's dive into the blobs. So shown here are the data abstractions for blobs, where you have your storage account. In this example, I have a storage account called Coho Winery. And then you can create inside your storage account one-to-many blob containers. And then you store your blobs into those containers. So all blobs have to be stored inside of a container. Now, what the containers provide is a level of sharing or basically access permissions for the blobs in that container. So here we have a container of images. We can put those pictures in that images container. Then we could set this container to be private, meaning only I have access to it with my secret key, or public, meaning that anybody can access it if they know the URL, or shared access can be provided via signed URLs. And I'll get a little bit into that in a few slides. Okay, so you create your blob containers, and then you can put your blobs inside those containers. Now, the underlying protocol that we provide is a REST protocol. So shown here is the URL that you use to actually access your blob in the cloud storage service. So you specify your storage account name. Blob will direct this to the blob service in the geolocation where your storage account was created. Container is the container name. No slashes can be in the container name, and the rest of the URL is the blob name. Okay. Now, in terms of the functionality that we provide for blobs, we allow you to upload blobs. We also allow you to update blobs. So if you actually just want to change a specific page or block of a blob, you can do that without having to re-upload the whole blob. You can get a blob, so you get the whole blob, or you can get a ranged offset in the blob. You can delete a blob, copy a blob within your storage account, and you also can create snapshots of your blobs. And this is actually very useful for creating backups of your blobs or additional versions of your blob. So you can actually have a blob, create a snapshot, update it, create another snapshot, update it. And the nice thing about this is that you're only charged for the delta differences between the different snapshots in the blob. So that's a nice feature in terms of the cost model. Now, another feature we have to provide is lease blob. This allows you to get an exclusive lease on a blob for exclusive write access. And you're able to renew that lease to continue that exclusive write access as long as you hold that lease. And this is great if you actually want to get basically a lease or a lock on a blob to do some modifications. But some services are actually also using this for doing things like leader election for masters and things like that for their service. Now, you can associate metadata with the blob, the standard HTTP metadata like cache control, content type, etc. You also can store your own metadata, name-value pairs up to 8 KB, and this metadata can be get and set separately from accessing the blob. So now I want to give an example of using the storage client library we recently released to access the blob service for your storage account. And so we're just going to give an example of creating a container and uploading and downloading a blob file. Okay, so the first thing you need to do is take that storage account that I talked about earlier that you created with the account name and the key you got back from the dev portal, and you create a storage credentials object. The next thing you do is you want to form a URL or URI specifying your account name .blobcorewindows.net, and then use both of these to create a blob client object. Okay? Now this blob client object will allow you then to do all the requests to the blob service for your storage account because it knows about your account name and the key. Now next we want to do is actually create a container. So we're going to derive from our blob client a reference which contains the container name we want to create. And this will create a blob container object. So with our blob container object, all we need to do is say create if not exist, and then if the container does not exist, it will be created in the cloud. Now, with that container, once it's created, we can actually derive from that container object specific blob objects that we actually want to manipulate inside that container. And that's what we're doing here. So we can take that container object and specify the blob name we want to manipulate inside the container, and we get a blob object. Okay? Now, when you actually do operations on blobs, you can actually specify a range of options when doing your request to the cloud service. These options allow you to specify the type of retry policy you want, timeouts, etc. In this example, we're just using the base options that are provided. So to basically upload a local file from my machine into the cloud, all I need to do is say, take the blob object, say upload file with a pointer to the file on my local machine, and we're going to use the default options, and this command will execute the upload into the blob service for your storage account. And it's basically derived from our blob client object using the container name we derived from there, as well as the blob name. Okay? Similarly, if you actually want to download a file from the cloud, all we do is actually execute for this blob we want to download, download to file. We specify a local file name, and then that will download the file to the local machine. And that's basically as easy as it gets to basically manipulate the blobs and containers in our blob service. Now, a few tips in terms of using the storage client library. One question we often get is, well, how can I get more throughput for my client? Well, one thing to note is that when you actually set up your client, make sure you set the default connection limit to something greater than 2. The default value with .NET is 2. If you want to get more parallel throughput, you need to set this to probably something times the number of cores you're using, times 12, 16, it depends upon your application. The other thing you can do, which is sort of obvious, which is, well, if you have lots of files you need to upload and download, you can upload and download them in parallel. But if you actually have some large files you want to get up into the cloud faster, we do have this option that allows you to specify, for this large file, how many concurrent uploading requests do I want to execute. So you're able to set with your blob client object the parallel operation thread count to, let's say, 4. This means that we'll actually use 4 concurrent requests to actually upload your blob. So what this means is we'll upload the blob, breaking it up into 4 megabyte chunks. Okay? So if you have a 10 gigabyte blob that you want to upload, we'll break that up into 4 megabyte chunks, upload it in parallel, and then commit that to be the readable version of the blob once all those blocks are uploaded into the cloud. Now note that this only works for blobs that are greater than 32 megabytes. Now another thing to note is that with the default blob request options, the timeout is set to 90 seconds per 4 megabytes. Okay? You might have a client that's remote around the world, way far away from the actual blob service where the blobs are hosted. So if 90 seconds isn't long enough, you may want to optimize that timeout to be the expected throughput that you would get from your connection, based upon the size of the blob you're going to upload or download. And finally, since this is a service in the cloud, you definitely need to make sure that you use a retry policy for your blob operations. Now, the default blob request options already wraps a good default retry policy and exponential backoff into the storage client library. So when you go ahead and execute your upload file or download the file, that's all wrapped there for you. But if you're programming the REST protocol, you have to make sure that you implement an efficient and retry and timeout policy. Okay. Now, one thing I want to mention is that we recently provided the access to Windows Azure blobs integrated with our content delivery network. So here's the scenario. You have frequently accessed blobs, and the blobs may be accessed by your customers around the world. And what you want to do, or what you could take advantage of, is actually caching these blobs in our Windows Azure CDN. And then that means that these cached blobs will be served from those edge locations to get the following benefits. You get better experience for users far from the blob service. So when you create your storage account, let's say, is located in US North. And if you have somebody from Europe accessing that, well, if it's actually cached in Europe, you'll get better connectivity and lower latency. And it's also very beneficial if you have high bandwidth content that you actually want to deliver for popular events. Okay? The Windows Azure CDN has 18 locations around the world, and it's actually very easy to use the CDN with your blob storage account. I don't have time to go into details, but the details of that are online. So just to summarize blobs before we move on to drives, a few things I didn't have time to go into in this talk, but are gone into more detail in other talks, is that we actually have 2 types of blobs under the covers. We have what's called a block blob. These blobs are focused on streaming workloads, where a blob consists of basically a sequence of blocks. Okay? And this type of blob works as follows. Basically, you can upload these blocks and then commit them to be a readable version of the blob. And you can actually update the blob based upon these blocks. So you can update the blob at the block level. So if you actually just want to change one block in the blob, you don't have to re-upload the whole blob. And the size limit for this type of blob is 200 gigabytes per blob. And at PDC, we provided access to a new type of blob called page blob. And this one is really focused at random read-write workloads, with the emphasis on efficient random writes. So you can do ranged writes across your blob. So here the blob consists of an array of pages, and whenever you do a write or a ranged write, it's actually committed immediately upon success. And these blobs can be up to 1 terabyte in size. Now there's a lot more details on these 2 types of blobs and examples for how they work and a deep dive on that in the PDC 2009 talk if you're interested. Then in terms of ways of accessing your content, I just summarized in the prior slide using our content delivery network. Another thing we provide access to is allowing you to give access to your blobs via signed URLs or shared access signatures. So what this allows is the ability to give access to a container or specific blobs via giving out a signature with a signed URL. So this gives you time-based access to your blobs. So you can give out time-based access without having to give out your secret key. And Matt will be giving a talk, I think, today in this room at 3 o'clock on using Silverlight with Windows Azure, where he'll be using signed URLs to access the blobs with Silverlight. And then I showed that you can actually access your storage account by saying your storage account name .blobcorewindows.net. Well, you could do that, but a lot of customers, they actually want to reference that with their own custom domain name. And so you're able to register custom domain names in the Windows Developer Portal and then use that to reference your blob storage accounts. Okay. And there's much more details about these online as well as in the PDC 2009 talk. So now I'd like to switch over to drives. The drives provide the ability for your application to mount NTFS volumes that are durable. So your Windows Azure application will be able to use existing NTFS APIs to access a durable drive that's mounted over the network. And the scenario and the benefits we're going after for this is that it enables the migration of existing applications that are already using NTFS APIs to be migrated easier to the cloud. And you also get durability and survival of your data if there's an application failover as well as if there's a hardware failure. Okay? So what a Windows Azure drive actually is, it's actually a page blob that's mounted over the network. So all your flushed and unbuffered writes to that drive letter are made durable to the page blob. So the page blob is actually a formatted NTFS single volume virtual hard drive that's mounted to your Windows Azure VM application. These drives can be up to 1 terabyte in size. No coincidence, it's the same size as the page blob. And when you actually mount a page blob for your VM application to use, and a page blob can only be mounted with 1 VM at a time, 1 VM instance for read-write access. But a VM instance can actually mount up to 16 drives at a time. Now, one of the nice things about this is that since the page blob is actually the mounted drive over the network, you can use the page blob interfaces to copy VHDs, upload them into the cloud. And for the drives that you're actually using in the cloud, you can actually download them via the blob interface and look at them locally. Because the drive interface is not naturally integrated with the blobs, because they are the blobs. Okay, so I just want to give a quick picture at a high level how this works. So assume we have a drive, a VHD, that's formatted as a single volume NTFS VHD, and we've uploaded it into the Windows Azure blob service called demo blob. Now, our Windows Azure VM application is going to try to mount this. When it mounts this blob, the first thing it will try to do, the driver will try to get a lease on the blob. If it can get a lease on the blob, it will then mount that blob and return a drive letter to the application. And then the application can then use that drive letter to just do normal NTFS API calls. In addition, when you do a mount, you also specify how much local cache disk space, how much local disk space on that machine do you want to set aside as a cache for the drive contents. So how does this work? Well, when you do writes, all NTFS flushed and unbuffered writes go to the page blob, they're committed there, and then return success back to the application. And if the data is in the local cache, the data will also be updated at that point in time. So all writes to the drive that are flushed are made durable to the page blob before returning success back to the application. Now, when doing a read, we first check the local cache. If the data isn't found there, we go to the blob service and then return it to the application and also update the cache. So on subsequent reads, if you get a hit in the cache, you can just return it to the application without having to go to the blob service. Okay. So now I'd like to just give a quick demo of how to actually use Windows Azure drives. And with this demo, what we're going to show, that's me, the blue Azure user, on the laptop here. We're going to show using a local VHD. Windows 7 has a nice management application called Disk Management that allows you to manage VHDs on your machine. We're going to have a VHD there. We're going to put some content in it, and then we're going to upload it into the cloud. Got it all hooked up to the internet. So let's see if this works. So then we're going to actually show running a a simple Windows Azure service to look at the contents of that drive. The service is going to allow us to list the drives that we have in our blob account, as well as look at the contents of it. And in doing this, I'll show the code for doing cloud drive initialization, mounting the drive, and unmounting the drive. So let's switch over to the laptop. I typed the password wrong. There we go. Let me set this something up here. Okay. So what I want to show first is bringing up the disk management application that's provided with Windows 7. So with this application, you can create VHDs, you can attach VHDs, and format them and mount them as a drive letter. So what I already did to save some time is I already created a VHD called demo VHD. You can see the VHD type here. It's 100 megabytes in size using this create VHD. And now I'm going to attach it to my local machine to use it as a normal drive. And we can see it attached here as a drive letter X. Now I'm going to come in here and then open it, Explorer. And so this file right here is actually attached as a drive for us to use just like any other NTFS drive. And so I'm going to come in here. Let's create a folder called MIX demo. And let's come in here, create a file called MIX file. And let's put hello mix in there. Okay, so we put a file, create a folder, put a file into this VHD. So let's go back to the VHD manager, and we can come down here and say detach. So this will detach the drive from my local machine. And now we're going to upload it into the cloud. Okay. So one thing about uploading this VHD is this VHD, let's get this out of the way. This VHD is 100 megabytes. And I could upload that whole 100 megabytes into the cloud, but there's actually around only 3 megabytes of that actually used at this time. The rest of it's actually just zeros. Now, one of the nice things about a page blob is that when you create the page blob, you specify what's the size that you want to create. In this case, we're going to specify 100 megabytes. But you only have to put into the page blob the pages that actually have data in them, because the other pages in that blob are considered to be initialized to 0. So in uploading this VHD, I don't need to upload the whole 100 megabytes. I only need to upload the pages that actually have data into them and insert them in the appropriate spot in that 100 megabyte virtual page blob in the cloud. So what I did is I built a little application using our cloud client library called VHD upload. And all this does is it goes through the VHD, finds the pages that are actually have data in them, and then it's going to upload those pages at that offset into that file. So we're going to upload the demo.vhd file to our xDrive demo storage account, blobcorewindows.net, into the drives container, and then into the file demo.vhd. And this is my secret key. Okay, so while this gets going, let's move over to the web service that I want to show. Now, in this web service, in order to use cloud drives, I'm going to just show a few things. One is setting up the storage account, and then initializing the cache that you have to do in order to use the drive, and then mounting the drive. So to set up the storage account, you come over here to your standard web role. Now, this is all provided with the standard Windows Azure SDK. I come in here, add a setting of a cloud storage account. I set up a connection string. And then in here, I can enter my storage account, xDrive demo, and then my account key. Okay. And then I can come to my web role and I'm going to add a static member here. Let's see, cloud storage account. Then I want to come down here and I want to initialize it to that configuration variable. So I'm going to say account equals cloud storage account dot from the configuration settings that cloud storage account. Okay. See if that compiles. Okay, succeeded. So this basically set up the web roles to actually use our storage account via this static member. Now the next thing I need to do is I need to allocate some local disk space for this role to be used as a cache for the drive. And we do that by going to the local storage for this web role and say, let's add some local storage. We're going to call it Azure Drive Cache. And we're going to say, let's specify we want to use 1 gigabyte of my local storage set aside for caching mounted Azure drives. Okay? And I don't want to click on this because I don't want the cache to be refreshed if my role restarts in this example. So I then can come over to my web role, and I need to now initialize the cache. So I'm going to create, for my cloud drive, first I'm going to actually create a local resource, Azure Drive Cache. And I'm going to take from the role environment variable we just created and get that information into this local resource. Okay. Okay, so then with this local resource, I now can access the root drive path when this VM instance runs, as well as what's the maximum size of this local storage. So I'm going to come in here and then initialize the cloud drive with that information. So I'd say cloud drive dot initialize cache, Azure drive cache dot root path, and I'm going to specify, let's put the cache files underneath a cache directory in that root path. And then I want to use all that local resource, that disk resource that I specified, reserved for caching Windows Azure drives. So I'm going to say Azure drive cache. Oops, let's use the maximum size of megabytes. Okay? Let's compile that. So this sets up my web role to basically be able to use a cloud drive, because I first have to actually set up how much of that local resource that I reserved can be used for caching drives. Now let's go back over here and look and see, okay, we uploaded the demo VHD. It was 100 megabytes in size, but only 3 megabytes of it was used. So we actually only had to upload 3 megabytes of that into the cloud. Now, the next thing I want to show is the web service that we have, as shown here. And this is already running up in the cloud. So I'm just coding up the service that we actually already have running. And I can hit refresh to list all the drives that have been uploaded. This is a drive I uploaded earlier. This is the new drive we just uploaded right now with the contents that we looked at. Now with this, we can mount the drive. And when I mount the drive, I can then look at the contents with this web service that I created. So let's just show that real quickly. So when I press this mount button right here, in order to mount the drive in my service, all I need to do is say cloud drive, drive equals web role dot account, create cloud drive, and then I need to specify the blob container and the blob name. So I'm going to specify the container drives. And then the blob name is actually going to be passed in with the button command name. Okay. So this sets up a drive object, which we then can use to actually manipulate that drive in the cloud. And so then we can say drive.mount. And here we specify how much cache space do we want to use for this specific mount. So we set aside 1 gigabyte of cache space For this specific mount, let's say we want to use 100 megabytes. Okay? And then you have to specify your drive options, and you typically want to specify none. We do allow a few other options. The first one allows you to do a check disk on mount, and there's more details about those on the web. Okay? Now, this will mount the drive, and then the one thing that's returned here is the path, basically the drive letter. Okay? So compile that. So this is all that you need to do in order to mount the drive. So let's go back to the demo here. So this is our running service in the cloud right now. This is the demo VHD we already uploaded. So let's mount it. It'll take a couple seconds for this to mount. Then once it's mounted, I've already written up code that allows us to access that mounted drive using standard NTFS APIs to look at its contents. So let's do that. So let's browse the disk using standard NTFS APIs. We can see the MIX demo folder we created, the file we created, and hello MIX. Okay? Then just to conclude the demo, when I press this unmount button, this will unmount the drive. And it's very easy to do that in your application. I'll just copy this down here to give me my drive object. Then all I need to do is say drive.unmount. And that's basically that's all you need to do. Okay? So that concludes the demo. So let's go summarize what we just saw. Okay. So in terms of the coding example, we just showed the ability of initializing your web service to be able to use a storage account, passing in the account name and the key. Then we initialize the cache space that we want to use overall for cloud drives that are mounted by this web role. Then for the example I went through, we uploaded a VHD into the cloud and then mounted it. Now you can also create cloud drives yourself in the cloud by just calling the create cloud drive API, specifying the page blob URI that you actually want to create. What this will do is actually will create that page blob given the size that you specify with create, and then format that to be a NTFS single volume VHD. So when you call create, that'll create the blob, format it for you. And then we went over how to mount the drive. You can then, once it's mounted, you can do your standard NTFS API calls. And one thing I didn't talk about is you can also snapshot the drive, similar to snapshotting a blob. So you can actually have a drive that's mounted, and you can snapshot it to keep creating backups of the drive. So that's very useful for that. And then you can unmount the drive. Okay. So in summary, the Windows Azure drives allows your VM instances to have access to this network-attached NTFS volumes. And one important thing here that sometimes gets confusing for some users is that the drives that are actually stored as page blobs in the cloud can only be mounted by Windows Azure applications in the cloud. Okay? This is because the drivers that we have that enable all this, as well as the NTFS redirection, are just running in the cloud at this time. So if you want to use the drives locally, you would download them via the page blob interface and then mount them like we showed earlier in the demo. As mentioned, the page blob can only be mounted by one VM at a time for read-write access. And then all non-buffered writes and flushes are made durable to that page blob. And as I showed in the prior slide, you can create snapshots or backup of drives. Okay? Now, one important scenario here that you can do is you can actually take a drive, create a snapshot of it, and then that snapshot can actually be mounted as read-only to multiple VMs. So if you actually want to serve up some static web content, you can actually take a drive that snapshot it, mounted by multiple VMs, and then serve up that content for some web roles. Okay. So that concludes a summary of drives. Now I'd like to move on to tables. Windows Azure Tables is our structured storage we provide that's sort of massively scalable. The tables can store billions of entities or terabytes of data, or tens of terabytes of data. And the programming interface provided with tables is what's now called WCF Data Services, was previously called ADO.NET. So this is, I think it's also called OData protocol. So this allows you to use .NET and Link to program your structured storage, as well as REST if you want to use any other program or language. Okay? So shown here are the table storage concepts. You have your storage account. In your storage account, you can create one-to-many tables. Here we have a table of customers, a table of photos, and then inside the tables, you can store your entities. Here we have entities of like name and email for customers, etc. Now, for the entities inside the table, each entity can have up to 255 properties. And the mandatory properties for every entity is the partition key and row key. Combined, these uniquely define basically the primary key for the entity. In addition, this also defines the sort order for your table. All the entities in your table are sorted by partition key and then row key within the partition. The other mandatory property is a timestamp, which we use internally on the servers to record when was an entity last updated. And this is used by the client to perform optimistic concurrency. Okay? So for the rest of the properties that are stored inside your entity, there's no fixed schema. So you can sort of think of this as a flexible schema table. All the properties are stored as name type value pairs. And the properties can be of the standard .NET type, string, binary, bool, datetime, etc. Now, one concept I want to dive into more detail are these two keys, the partition key and row key, in particular the partition key. This is very important if you're going to use Azure tables. Every table that you define has a partition key. You can sort of think of this as the first column of your table. This is also the first sort order of your table. This is used to basically group your entities into what we call table partitions. All the entities in a table that have the same partition key value are grouped into the same partition. Okay? And then all of those entities in that partition are then sorted by the row key. So the row key provides the uniqueness within the partition. Now, the reason why we expose this to application developers is that this allows the application to control the granularity of those partitions for the table. And this ultimately controls the scalability of the table too, as well as controls what you can actually do in terms of batch transactions, which I'll talk about in a second. Okay, so the purpose of the partition key is it allows you to do three things. One is it provides you entity locality. All the entities that are stored into the same partition will be grouped together and stored and accessed from the same table server. So you get efficient querying and cache localities for those entities within a partition. More importantly, the partition provides a level of batch transactions for atomicity. So it allows you to do what we call entity group transactions, where if you have a set of entities, if they have the same partition key value, then you can actually do an atomic single batch transaction across all these entities at the same time, or actually up to 100 entities at a time. So you can do multiple inserts, updates, and deletes across these entities and have that performed as a single transaction to the server, but only if their entities are in the same partition. The other thing that this helps define for your table is the table scalability. So you have your table, you have your entities in it, and we monitor the usage patterns of your partitions. And then if a set of partitions in your table is getting too hot for the servers to handle, we'll automatically split these partitions out and serve them across other servers to meet the traffic demands for your table. So let's just go through a quick example. So here we have a table of movies where the first column is a partition key representing the category of movie. The second column is the row key representing the title. We have our timestamp, and then we have some additional properties. Now, all the entities that have the same partition key value represent a table partition. So here we have a table partition of action entities, a couple animation, etc. Now, what we do is we monitor the access patterns to these different partitions. So let's assume for this example that the first half of the table, up through animations, getting about half the traffic for this table. And the second part of the table is getting the other half. Okay? But now let's say for this single server A, that's too much traffic for it to handle. So what are we going to do? Well, we can actually split this table into what we call range partitions at partition boundaries. So we're going to split this after the animation partition into two range partitions and serve them on separate servers. This is all done automatically under the covers for you. So you can see here, we now have server A that will serve for the table movies all of the partition key ranges from min key to comedy. And then server B is from, but not including comedy. And server B is from comedy to the max key. Okay? So this is important to understand because it basically, the granularity you choose for your partitioning is the granularity that will allow us to automatically scale out access to your table. If you put all of your entities into a single partition, meaning that they all have the same partition key value, that may be great for your application in that you can do atomic transactions across all those entities. But we can't split your table across these servers. On the other hand, if you go to the other extreme, if you actually define a separate partition key for every single entity, that's fine. And we support that. And that gives us sort of endless opportunities to basically split your table across different servers. But you wouldn't be able to benefit from the entity group transactions. So it really depends upon what your application is trying to do in terms of what's the granularity you want to choose for your partition key. Okay. So in terms of the table operations, the table you can create tables, many tables, list them, query them, delete them. And then for entities, you can insert entities, update them. We support two types of updates, where one is you can merge the changes into an existing entity, or you can replace the entity. You can delete the entity, you can query them in the table. And we also, as I mentioned, we support these entity group transactions. So now let's go through an example using our movie table to just show quickly how you actually use the storage client library to program tables. Now this is actually layered on top of WCF data services. So it's basically using WCF data services to do most of all the heavy lifting there. To talk to our table service. The first thing we're going to do is create a class that represents the entities that we're going to be manipulating in this table. So the class is called movie here. And as I mentioned, we have three mandatory properties you have to have defined to use Windows Azure tables. First, the partition key. And for this partition key, we're going to use the movie category. Then the row key is going to be the title. Date timestamp for the optimistic concurrency, and then the rest of the properties can be whatever you want, in whatever type you want. Release year, the rating of the movie, whether this is a favorite movie or not. Now, the other thing you need to do in terms of tying this into WCF data services is you need to specify this data seeker key annotation. What this tells the data services is that these two properties represent the primary key for this entity. Okay. So once you've done this, we can now use this movie object to insert and update entities into our table. So let's show that. So in using the table client library we're going to do the same thing we did with the blob example at the beginning, where we set up our format string. And to access the table service, what you're going to be doing is specifying your count name .tablecorewindows.net. And then you specify your credentials, just like you did with the blob example, and then you create a table client. You then use this table client to create context objects in order to access the table service. So let's do that. Well, first we're actually going to create a table called movies with the table client. So we have the table name called movies. We take our table client. We then can say create table if not exist, and that will create the table if it does not exist for our storage account. Okay, now we're going to use the table client object to create context, data service context for us to manipulate entities for our storage account. So we call the tables client object and say get data service context, and this gives us a table context. This table context will allow us to then actually manipulate any table in our storage account and add objects into it. Here we're going to add objects into our movies table, and we're going to create a new object. So let's assume that the constructor takes action as a partition key and Whitewater Rapids as the row key, and the rest of the properties have some default values. So this will add an object to that context. At this point in time, this context is not uploaded into the cloud. It's not until you actually do save changes that you actually do the transaction from your client to the table service to basically do this insert. And note, we actually wrap WCF data services with a save changes with retries. So this basically wraps their save changes with a retry, in that if there's a connection failure or timeout or server busy, we'll retry up to 3 times. And this retry also has built-in exponential backoff for you. And this is provided with the storage client library. So now let's say we've uploaded and inserted a bunch of movies into our table. And now we want to query over that table using a link query. So that's shown here. So you can write your standard query using link, where we're going to query in this example from the movie table that's specified here. And it specifies the type of object that's going to be used. Then we're going to query, give me all the entities where the partition key equals action and the movie rating is greater than 4 out of, let's say, 5. So this means that we're going to get some good movies back. Then we actually wrap this query with an as table service query operation that's provided by our storage client library. Now what this does, it does a few things. One, it does retries for the query, and also with exponential backoff. But it also hides this concept we have for the table service called a continuation token. Now the table service, when you actually do a query, it will return at most up to 1,000 records, 1,000 entities at a time. And it also returns a continuation token. So if you get one of these continuation tokens back, you have to redo the query with a continuation token, and it will continue where it left off. Okay? And this is all wrapped for you in the storage client library by attaching to your query an as table service query. Okay. Now here we have our link query. At this point in time, we actually haven't done the query to the table service yet. It's not until we here do a for each that we actually go off and do the table service query using link in WC data services. So this will go to the table service, get the entities back that match this query, and allow us to traverse over them. So let's say as we traverse over them, we want to update them to mark them as favorite, just as an example. So we're going to mark the movie as favorite, and then we're going to say update the object in our context. Okay? So when this for loop is done, we have basically retrieved all the entities that matched our query and updated them. We haven't actually stored any of them back to any of the updates to the table service. So to store the changes back to the table service, we can say context.saveChanges with retries again. And this will actually push all the updates to the table service. Now one very important point here is that if you just use the base save changes with retries without any parameters, this will push each update one at a time. Okay? Might not be the most efficient thing for your application. But if you actually say save changes options.batch, this will actually batch these together and then send them all together as a single transaction to the storage service. Now there's one limitation here in that this will only batch up to 100 transactions at a time. So you have to correctly deal with that logic, which I ignored for this simple example. Okay. Questions at the end? Oh, questions at the end? Yep. So table tips, just to go a few things in terms of using the table. Again, you want to set your .NET connections to greater than 2 if you want to do multiple outstanding requests at a time. Now, again, if you're actually programming to this with the standard WCF data services without using our storage client library, or maybe programming against it with REST, you need to make sure that you program with retries and exponential backoff. If you're using our storage client library, this is automatically provided for you with using save changes with retries and the as table service query for the queries, as I talked about earlier. Now, one interesting thing is that because of retries, when you do an insert of an entity or a delete of an entity, you might see this strange behavior where you know the entity was not there when you did the insert, or you know that it was there when you did delete, but you get back a conflict or not found. So what happened? Well, with retries, the original request to the table service might have completed. Okay? But due to a connection failure or whatever, the success result was not returned back to the client. So the client will retry. And then it will go back there and say, oh, wait, the entity is already there. Or for a delete, the entity doesn't exist anymore. So you need to make sure that your application successfully handles these conflicts that you can get back when doing retries. Then finally, one thing that we've seen some patterns that some applications exhibit is this append-only pattern for inserting entities into a table. And this often occurs if the table's partition key is just a timestamp. So if you imagine you have a table where the partition key is the timestamp, and you keep on inserting the entities based upon the current time. Okay? So you keep on inserting the entities. Now, sort of picture in your mind what would that look like? Well, you have a table, and maybe these tables are spread across different servers. You have this one on one server, the middle part of your table on another server, and this other part of the table is load balanced on this other server. Well, in terms of this table, it's sorted by your partition key. So if you keep on inserting entities based upon the current time, you're going to keep on inserting them, effectively appending them at the table, at the end of the table. So this means that you'll effectively be inserting them into this one table server. So if you're trying to get massive amount of insert throughput, that's not going to scale with the partitioning system that we have. So if you actually want to get thousands, multiple thousands of requests per second, you need to have a scheme for your partitioning that allows you to insert across your table. Because we'll load balance your table across all these servers based upon the partition key. And you basically want to be able to insert into these tables to get the full throughput for a massively scalable table. So if you want to use a timestamp, what some applications end up doing is basically using a prefix in front of the timestamp to help them basically insert across the table. Though it does make other things a little bit more complicated in terms of maybe the type of queries they want to perform. Okay, so that concludes tables. And now I want to summarize with queues, giving a quick overview of that. Shown here are the storage concepts for queues, where you have your storage account, cohort winery, and it can create one-to-many queues. In this example, I created a queue to process the orders that we might get for the winery. And then we put the work items that we want to process into a message. So an example message could be customer ID, order ID. We could have even additional links to other URLs or other even blobs. Okay? So at a high level, what does a queue provide you for your web applications? Well, it enables you to do this workflow, loosely coupled workflow between your roles. Okay? So when you use a queue, the web roles in this example might be taking some work items in. It can in-queue those work items into a queue, and as soon as the items are stored in the queue, it can basically forget about it. It knows that once it puts the item in the queue, it's going to be stored there reliably for a worker to come and consume it. Okay? Now, what the queues provide is this concept of guaranteed delivery and processing of messages for your application. And this really consists of a two-step process, and I'll just quickly go through that. So the first step is that, let's assume we have some messages that are in-queued and put into the queue. Now a worker comes along and it's going to dequeue the message. When it dequeues the message, the dequeue operation marks that message as invisible for an invisibility time that the application defined. Okay? The message is still in the queue, but no other workers will see it when they try to get a message. Okay? And it's going to be invisible until that time passes. Then the worker has until that time to process the message and then delete it. If the worker deletes the message, it'll be deleted from the queue, and no other worker will ever see it again. Okay? But if the worker crashes partway through processing the message, we don't want to lose that message. And so the message will become visible after that invisibility time for another worker to process that message. So that's what we mean by the queue providing this guaranteed delivery and processing of messages. And it does that through this invisibility time concept. So let's go through a quick example of how we use the queue client library to program queues. Here again, we create our base URI, which is our storage account.queue corewindows.net, to point these requests to the queue service for your storage account. You then create a queue client object with that base URI and the credentials, where the credentials are your account and your key object that was shown on the blob code example earlier. And then what we want to do first here is from the queue client, we want to create a queue object. So we pass in the queue name at the end there that we want to create, and that defines a queue object. Then we can say create if not exist. And let's say now we want to add messages into that queue. Well, we can create messages using the cloud queue message object, and then we do queue.addMessage basically that simple. Now, there's one thing I want to point out here, which is a pattern that we've seen by some applications, is that we're watching these applications come, and we keep on seeing these requests saying that queue already exists, queue already exists, queue already exists. It's because they're put in their loop from their worker role, from their web roles, when they're in queuing items, right before they do add message, they have queue.create if not exists. So for every message that they're in queuing into their service, they're going to try to create the queue over and over again. Yeah, it'll guarantee that the queue's there, but you'll be doing lots of extra requests that you're paying for. Okay, so just to point that out. So you want to create your queue once, and then insert messages in it. Okay, now for a worker to get the message, they just take the queue object and say get message. And as I mentioned, when you get the message, you specify this invisibility timeout. This means that when you dequeue that message, and we also support batch dequeues, where you can dequeue up to 32 messages at a time, these messages will be marked as invisible, in this example, for 3 minutes. So we have until 3 minutes to process the messages and then delete them. So, and this is how we would delete the message. Okay? If the messages were not deleted within that amount of time, they would become visible again for another worker to process them. So just to summarize queues, giving a few queue tips here. The messages that you actually store can be up to 8 KB in size. If you need to store a message larger than that, you can actually store the message's content in maybe a blob and then store the blob reference inside of the message. Now, due to the invisibility time concept and worker roles crashing, messages may be processed more than once. So you really want to make sure that your message, your work items that you put into the message are idempotent, which means that they can be repeated and potentially repeated multiple times. Now, we tried to give an approximate FIFO for the queue, but it's not guaranteed at all because of this invisibility concept as well as dealing with a largely scalable storage system. So you should assume for your service that messages that you put into the queue can be processed in any order. Then one request that we get from some customers is that I have a queue, but I want to get more throughput from it. So the target design point for a single queue right now for us is around 500 requests per second. Of course, it depends upon the workload that you're putting against the queue. Now, if you want to go higher than a queue can actually handle right now, what some applications are doing is they batch multiple work items, let's say from their web role, into a single message. And let's say if you batch 10 work items into a single message, then that means that you just got 10 times the throughput for the queue, effectively. It does mean that your worker now will be processing 10 messages at a time instead of 1 message at a time. And so you have to deal with that. Similarly, they might actually put several messages into a blob and then put a blob reference into the queue. Whereas in some applications, the route they've gone is they basically manage multiple queues. And then they have some sort of policy, let's say round robin, in terms of what web roles, for the queue that a web role in-queues in, as well as what queue a worker will dequeue from. Then I also want to point out 2 additional attributes that we provide with queue. One is dequeue count. When you dequeue a message, you get back also its dequeued count. So if a message you got back, let's say it was dequeued several times, that's a hint that this message might be a problem. It means that the workers are not able to process it within the allotted time, or maybe it's crashing the workers. So you may want to take a message with a high dequeue count, put it off into another queue you process differently, or a table to look at later. And finally, you're also able to monitor for a queue the approximate number of messages in the queue. And this is very useful for potentially scaling up or scaling down the number of workers you have. So if if you actually look at the queue and it's overflowing with messages, you may want to spin up some more workers. If the queue's basically empty, you may want to spin down the number of workers you have. And we provide management APIs in Windows Azure to make it easy for you to spin up and spin down those roles. Okay? So in summary, what I wanted to accomplish today is give you an overview of our blobs, drives, tables, and queues, and show you hopefully how easy it is to program these with our storage client library. All this is available in the cloud right now. Go to our website if you haven't already. Check it out, and please check it out. Okay, there's evaluation forms that were on the seats. Please fill them out and return them in. I actually ran out of time here. So what I'm going to do here is let's just end the talk at this time, and then I'm just going to stick around up front. I don't want to keep you from lunch, and I'll stick around up front as long as needed to answer questions. Okay, thanks.